What if I told you there's a train that doesn't touch the ground? No wheels, no friction, just pure speed, flying on magnetic force at 500 kilometers per hour. Hidden deep inside Japan's mountains, engineers are secretly building one of the most advanced technologies on Earth, a 43-kilometer-long magnetic levitation track that will soon connect Tokyo and Osaka faster than any bullet train ever could. This isn't science fiction. It's real. A train that floats 10 centimeters above the track, powered by superconducting magnets so strong they can lift tons of steel in total silence. No engine roar, no vibration, just pure, smooth levitation at half the speed of sound. But here's the shocking part. Despite being decades ahead of its time, Maglev technology has barely made it out of the lab. Only one short commercial line exists in the entire world. So, what's stopping this futuristic train from changing the way we travel forever? Is it too expensive? Too dangerous? Or are we simply not ready for it? In this video, we uncover the untold truth behind the world's fastest train, the Japanese superconducting Maglev. How it floats, how it moves, and why the future of transportation might be hiding deep underground, waiting to rise. To understand how Maglev works, let's start with the magic word itself. Magnetic levitation. Two forces, attraction and repulsion, are the key. Maglev trains use one of two primary systems to float above their tracks. The first is called electromagnetic suspension, or EMS. In this method, powerful electromagnets are attached to the underside of the train. These magnets attract the train upward toward the steel track above it. It's a delicate dance, too little magnetic pull, and the train falls. Too much, and it slams into the rail. To stay stable, EMS trains constantly adjust their magnetic field thousands of times per second using feedback loops and sensors. The levitation gap is just 8 to 12 millimeters, roughly the thickness of a pencil. The system works, but it's unstable and complex. One wrong reading, and the train could wobble or fail. That's the technology used in Shanghai's Maglev, the only commercial high-speed line currently in operation. It's just 30 kilometers long, connecting Shanghai Airport to the city center. It takes 8 minutes to complete the journey. Fast, yes, but too short to unleash Maglev's true potential. By the time it hits its top speed of 430 kilometers per hour, it already needs to slow down again. Its average speed, 225 kilometers per hour, is actually slower than many traditional bullet trains. So Japan decided to go a different way. A more stable, more ambitious, and far more complicated one. Stick around. More fascinating stories are coming your way. Instead of pulling the train upward with magnets, Japan's engineers chose to push it upward, using a technology called Electrodynamic suspension, or EDS. This system uses superconducting magnets on the train and passive coils along the track. When the train moves, its magnetic field induces electric currents in those coils, which in turn create opposing magnetic fields, pushing the train upward. It's a self-stabilizing system. If the train drifts too low, magnetic resistance increases and lifts it back up. If it goes too high, resistance drops, letting it settle again naturally. The result? A 10-centimeter levitation gap, nearly 8 times larger than the Shanghai system, and it's inherently stable, even in earthquakes. But there's a catch. EDS Maglev doesn't work when standing still. It needs motion to create magnetic lift. That's why Japan's L0 series Maglev uses retractable landing wheels. They drop down during slow speeds and tuck away once the train surpasses 100 kilometers per hour, allowing it to float freely on magnetic power. At full speed, 500 kilometers per hour, the train literally flies without wings. Don't go anywhere? The best is yet to come. To generate a magnetic field strong enough for this miracle, Japan's engineers rely on superconducting coils, made from niobium titanium wires, kept at temperatures near absolute zero using liquid helium and liquid nitrogen. Why? Because at such low temperatures, superconductors allow electricity to flow with zero resistance. That means no wasted energy, just pure magnetic power. Each Maglev car houses 8 superconducting coils, 4 on each side, arranged in precise polarities to shape the magnetic field. But maintaining such cold temperatures inside a moving train? That's no small feat. The system uses a pulse tube refrigerator, a technology so advanced it's also used on the James Webb Space Telescope to cool its infrared sensors. Here's how it works. It creates standing sound waves inside a sealed tube. The pressure differences between peaks and troughs move heat from one end of the tube to the other. The hot side dissipates heat into a radiator, while the cold side keeps the superconducting coils chilled, all without moving parts or compressors. It's one of the quietest, most reliable refrigeration systems ever built. A symphony of physics keeping a 300-ton train floating silently through the air. Keep watching for more mind-blowing insights. But these powerful magnetic fields, some 50,000 times stronger than Earth's own field, create a serious problem: passenger safety. You can't have people sitting next to MRI-level magnets without protection. So, engineers had to figure out a way to contain those fields. Magnetic fields can't be blocked, but they can be redirected. Just as copper wires guide electrical currents, iron can guide magnetic flux. Iron has low magnetic reluctance, meaning magnetic fields naturally prefer to flow through it. Using electrical steel shielding, Japan's engineers built a magnetic tunnel that redirects fields away from the cabin and stations. This steel is made with 3% silicon, cold-rolled to align its grain structure in one direction. That alignment lets it carry 30% more magnetic flux, perfect for shaping the field exactly where engineers want it. By carefully flipping magnetic poles and using mirrored coil patterns, they even created magnetic bubbles, zones of minimal field strength inside the passenger area. The result? Inside the cabin, the magnetic field is reduced to just 0.5 millitesla, about the same as Earth's magnetic field. Completely safe. It's one of the quietest and most stable environments you can travel in. Even though just inches away, unimaginable magnetic forces are at work. We've got more incredible content on the way. Stay with us. Now comes the next mystery. If the train floats, how does it move forward? The answer lies in something called a linear motor. Imagine taking a normal electric motor, the kind that spins a wheel, and unrolling it flat. That's a linear motor. In a maglev, the train's onboard magnets act as the motor's rotor, while the coils embedded in the track act as the stator. By alternating the current through these coils, engineers create a wave of magnetic attraction and repulsion that pulls the train forward. It's like the train is surfing a magnetic wave that's constantly chasing it. When it needs to brake, the system reverses the magnetic sequence, creating a regenerative braking effect that sends power back into the grid. At low speeds, the train relies on its wheels and air brakes, but at high speeds, the linear motor does it all. No contact, no wear, no noise. You might wonder, if it doesn't touch the track, how does the train get electricity? For lower-speed maglev systems, a third rail provides power directly. But at 500 kilometers per hour, that's impossible. Friction and heat would destroy the system. Early prototypes used onboard gas turbines, but the final L0 maglev collects energy inductively, through the very same magnetic fields that propel it. It's like wireless charging on a massive scale. Each car harvests energy from the track coils, enough to power onboard systems and maintain its superconducting magnets. This creates a slight magnetic drag, but far less than what wheels would generate through friction. It's an elegant solution, clean, efficient, and silent. More amazing facts are coming up next. Don't miss out. Japan's obsession with high-speed rail began decades ago. In 1964, the country stunned the world by launching the Shinkansen, the world's first high-speed train, connecting Tokyo to Osaka. It was fast, reliable, and safe, and it completely transformed Japanese society and business. But engineers immediately began dreaming bigger. What if they could make the 4-hour journey even faster, under 1 hour? By the 1970s, Japan National Railways began testing Maglev technology. At a small facility in Miyazaki, they built a 7-kilometer test track. Early prototypes hit 60 kilometers per hour in 1972, and by 1995, they reached 411 kilometers per hour. In 1990, construction began on the Yamanashi test track, a 20-kilometer section nestled between Tokyo and Nagoya, right along the route of the future commercial Maglev line. Here, they tested the full-scale L0 series Maglev, capable of carrying 700 passengers in 12 cars. In 2015, it set a world speed record, 603 kilometers per hour. The dream was no longer theoretical. It was real. But building perfection comes at a price, a very, very high one. The first phase of Japan's Maglev line, connecting Tokyo to Nagoya, spans 285 kilometers and is set to cost an estimated $13.7 billion. That's $77 million per kilometer, compared to just $2 million per kilometer for France's TGV rail system. Why so expensive? Because 86% of the line will be underground. To achieve the most direct route, engineers are boring through mountains, over 200 kilometers of tunnels. This not only drives up costs, but also increases drag and energy consumption. In open air, the train slices through the atmosphere cleanly. In tunnels, air has nowhere to escape. It compresses, creating resistance. As a result, the Maglev uses 30% more energy than Japan's fastest Shinkansen. Still, it's vastly more efficient than flying the same route. But for a 1-hour time savings, the economics are tough to justify. So far, the world has been cautious. China's Shanghai Maglev remains short. South Korea has small test lines. Germany's Transrapid system never went commercial. And in the United States, even traditional high-speed rail remains a political and financial struggle. Maglev's costs and the need for brand-new, magnetized tracks make it even harder to sell. For example, in the US, a Maglev between New York and Los Angeles could theoretically cut cross-country travel to 7 hours. But the cost? Astronomical. Hundreds of billions of dollars. Maglev's true sweet spot lies between cities 200 to 800 kilometers apart. Distances like Washington, D.C. to New York, or San Francisco to Los Angeles. In these corridors, Maglev could outperform planes and cars easily, saving not just travel time, but billions in productivity. But governments must first decide, is shaving 1 more hour of travel worth multiplying the cost tenfold? Despite the challenges, Japan presses forward. By 2027, the Tokyo-Nagoya line is scheduled to open. The full route to Osaka should follow in the 2030s. And beyond that? Perhaps one day, superconductors won't need liquid helium. Perhaps room temperature superconductors, if they ever become practical, will make Maglev cheap enough to spread worldwide. It's easy to dismiss Maglev as over-engineered, a luxury experiment. But history has shown that today's experiments become tomorrow's standards. Steam to diesel, diesel to electric, electric to levitation. Every leap forward once seemed unnecessary, until it wasn't. For now, Maglev remains a symbol of what happens when a nation dares to imagine something better. It's a floating promise of silent speed, clean energy, and near-effortless travel. Whether it becomes the backbone of future transport or remains a glittering engineering marvel, it proves one thing beyond doubt. Human ingenuity never stops trying to defy friction. If you enjoyed this deep dive into the world of Maglev trains, make sure to like, subscribe, and share. because the next era of travel might not happen on the ground at all, but above it.